Hello there, and thank you for watching. I'm Christopher Apodaca, and I'm going to be covering the ins and outs of Dijkstra's algorithm. Dijkstra's algorithm is a method employed to find the shortest distance between any 2 points on a graph of weighted vertices. These vertices, or nodes as some people tend to call them, are connected by what are known as edges. Indicated by lines with corresponding numbers associated with them, each one of these edges are weighted. That is to say, they have some kind of cost associated with them, and Dijkstra's algorithm can be used to find the least cost path between any given vertices. Dijkstra's algorithm is considered a greedy algorithm. Greedy algorithms are those which make the most optimal choice at each given step or iteration during operation. That being said, when Dijkstra's algorithm is performing its search for the most optimal path, it does so with the least costing edge in mind as it traverses the graph. Let's go ahead and take a look at a common problem here. Consider the map of the United States. Now let's assume we need to travel from New York to LA in the shortest amount of time possible because we're in a big hurry. How could we possibly solve this problem? Dijkstra's algorithm has got a solution for us. We can start off by marking the cities as vertices, which essentially is circles with names in them. And we would then connect these cities with lines, or edges. We could, for example, weight the edges by the number of hours it takes to travel between each city, and then we can implement Dijkstra's algorithm. Algorithms are a lot like recipes. So let's go ahead and consider what we'll need for this algorithm to work in terms of tools. We'll need a weighted graph, a source, which is our starting point, a target, which is our ending point. We'll need a set, and we'll need a queue. To help us implement the algorithm, I went ahead and compiled some pseudocode to better lay out what it is we're trying to accomplish here. First of all, we're going to go ahead and set our starting node's cost to 0. Secondly, we'll set the costs to all of the other nodes within the graph to infinity, or some arbitrarily high number. Now we'll need to employ our queue of nodes. Let's fill it up with all the nodes within the graph. Now the idea is pretty simple. We hop into a while loop that terminates when we finish dequeuing all the nodes in our queue that we filled up. We'll want to grab the node with the smallest cost first, during each iteration that is, and we'll push that to our visited set because we just viewed it. Now we'll check all the neighbors and compare their cost plus the edge weight connecting them to the current smallest node. If the value of the current smallest node's cost plus the edge connecting them is less than the current cost of the neighbor, we'll update the neighbor's cost. If not, we leave it alone. We continue this until there are no more nodes within the queue, and then we're done. Here is some better pseudocode, a little bit more professional looking, for a reference. Remember that graph from earlier with the US mapped out on it? Let's consider those cities as nodes on our graph, with edges weighted like so. Considering that we are interested in traveling from New York to LA in the shortest amount of time possible, let's go ahead and set up the problem so we can solve it using Dijkstra's algorithm. Firstly, we mark our starting point, which is A. Then we set all the costs of the nodes to infinity, or some arbitrarily high number. And now we're ready to consider our options. We'll need to check A's path first. So A to B costs 3, which is the smallest. So let's investigate this. We update the cost of B only if 3 is less than the current cost of the neighbor, which is infinity. So 3 is less than infinity, so we update B. Now let's consider A to C and A to D. A to C costs 7, which is less than infinity, so we update that cost. A to D costs 9, which is less than infinity as well, so we'll update that cost chart too. All of A's edges have been examined, so let's move on to B. B to C, the B cost is 3, and the edge cost is 1. So 1 plus 3 is 4. 4 is less than 7. Now we're going to put the edge cost in the column, which is 1. Now consider the path B to D. The B cost is 3, and the edge B to D is 3. So 3 and 3 is 6, which is also less than infinity. So we update the cost with the edge weight. Now we only need to compare C to D. We must first consider C's current total cost. This looks like 1, but we have to remember that it was just the edge B to C, so we have to take into account the total cost all the way back to A. So we take CB, which is 1, and add BA, which is 3, and we add the new path CD2, which is 6. And 6 is not less than 6, so we do nothing, and we are done. Hopefully this presentation has helped you understand Dijkstra's algorithm in a little bit more detail. I hope you enjoyed yourselves, and thank you all for watching.